Hi there, my name's Chris Collison, and we're going to continue today with CHMP 442. That's quantum mechanics in chemistry at RIT. And today we're going to finish up the general principles and add some bits and pieces that come from chapter 4 of Donald Macquarie's textbook on quantum mechanics. So we're going to take a look at angular momentum and consider that as a vector quantity and think about how we're going to generate the operators for angular momentum. We're going to also look at orthogonality, and we're going to see what that means. And we are going to consider the Kronecker delta. And lastly, we're going to look at a shorthand notation for writing down these integrals, and we're going to call that the BRA-KET notation that Dirac introduced. So let's try and tie up all these loose ends as we come to a close in chapter 4. Thanks for listening. So let's go through some of these bits and pieces, starting with angular momentum. So here's the context. So every observable has a quantum mechanical operator. So what are the quantum mechanical operators for angular momentum? So let's actually first think about angular momentum a little bit. So we have a body that is moving in a circular motion in the xy plane. So we know that linear momentum is a vector quantity. And that would be given by mv, or simply p arrows. So these are vector quantities. What else can we say about this body moving through circular motion? We're going to use the new term in here to denote the frequency of rotation, and that's in cycles per second. What else? Well, we also know, of course, that speed or velocity is distance per second. We also know, well, let's write that down first of all. The distance we're talking about here is the circumference of the circle that the body is moving round in that circular motion. So that circumference is 2 pi r. And then we've got this frequency in here. So the frequency gives us the per second piece, and the circumference gives us the distance, right? That would be in meters. So this ends up being our speed or our velocity. It is a velocity because it's a vector quantity, right? That velocity is changing all the time because of the circular motion. We can also think about the angular speed, and that angular speed is equal to 2 pi nu. We're also going to call that omega of rotation, which is also equal to v divided by the radius r. How do we know that that is true? V is equal to r omega rotation, and so therefore omega of rotation is equal to that v over r term. What else do we know in here? Kinetic energy is equal to half mv squared. So now we can substitute for v, because v is equal to r omega. So this would be equal to 1/2 m r squared omega squared. And it turns out that that is also equal to 1/2 I omega squared. Where now this I, the I in here, is what we call the moment of inertia. So we've got some correspondences here that I'm going to talk about. We've got a correspondence for velocity, because we've got omega in the circle that corresponds to v in a straight line. We also have mass, and the correspondence here is actually inertia in circular motion, and mass m for linear motion. Let's go over here. We've got kinetic energy. So that's equal to 1/2 I omega squared for circular motion, and that corresponds to 1/2 mv squared for linear motion. And lastly, momentum. We have I omega, so it's like, you know, the mass. Here we were expecting mass times velocity, so for a circular motion we get inertia multiplied by the angular speed, angular velocity, and that corresponds with, in linear terms, mass times velocity itself. And so also momentum, by the way, is equal to, let's break this down a little bit, right? So we've got m r squared v over r. So because the moment of inertia here is equal to mr squared. So here's our moment of inertia. I is the moment of inertia. It's equal to mr squared. And of course the angular speed here is equal to v over r. So that's the angular speed over here. And that ends up being equal, of course, once the r's cancel, is equal to m times r times v. So let's explore that a little bit more in the next slide. So angular momentum, therefore, is L equals I omega equals mr squared times v over r equals mvr. So angular momentum is proportional to the mass. It's also proportional to the distance from the origin, right, the radius. We also note, as I mentioned in the previous slide, so the kinetic energy is equal to I omega squared over 2 equals I omega squared over 2I, which is equal now to angular momentum squared over 2I. So we've played around so far in this little lecture with angular momentum. I've kind of introduced it to you. We've added a few equations. We've taken a few equations away. But I'm also going to now put forward a definition for angular momentum in terms of vectors. So let's change color for that. So let's say definition of angular momentum, and that is r, the position vector, multiplied by the momentum vector, is equal to the angular momentum vector. And these are all vector quantities. P is also, by the way, equal to mv. And as I mentioned before, r is the position of the particle from a fixed center. So a little bit of let's see, a little bit of vectors, vector mathematics here. We're going to remind ourselves that the vector product of two vectors, so often this is called the cross product, is given by the following expression, where these values I'm drawing are the magnitudes of those vectors, the scalar length, if you will. C is a unit vector perpendicular to the plane formed by u and v, and theta is the angle between u and v. So it turns out that when we think back to our definition up here, this vector for angular momentum is a vector perpendicular to the plane formed by the radius and the momentum, those vector quantities. So what else is implied by this? So let me just finally state, and that this angular momentum is basically the angular momentum that we describe is in a direction that's perpendicular to the plane that contains the circular motion. So this is what I drew in the previous slide. So noticeably, right, so let's look in red here. So if we've got motion in this xy plane, the angular momentum is actually going to be pushing in the z direction. And so we can actually write this down in three different ways. If we break down the angular momentum for any body moving in a circular direction, we break it down into its component pieces in the x direction and the y direction and the z direction. Let's take a look at what we get. We've got L sub x is equal to y p sub x minus z p sub y. We have Ly equals z p sub x minus x p sub z, and Lz is equal to x p sub y minus y p sub x. And of course, if we want the operator for angular momentum in the z direction, what we can do is we substitute in the operators. So we've got a position operator and we've got a momentum operator in here. So of course the position operator is simply x multiplied by x, so we're going to keep that in here. We're going to add in, of course, the operator for linear momentum here, which is going to be minus I h bar di by di y, and then we've got minus, again we've got operator for y in here multiplied by minus I h bar di by di x, and that comes from this in here. So we're inserting operators now, so the final operator that we end up getting, okay, is equal to minus I h bar x di by di y plus minus I h bar y di by di x. So that's the, I'm going to check this out in page, of course, page 148, table 4.1 of your textbook, and that's the operator for angular momentum in the z direction, at least with Cartesian coordinates. We'll think a little bit more about spherical coordinates as we move through the rest of the course. So that's a little introduction to angular momentum for you. It's addressed in section 4, chapter 4 of your textbook. So let's go on now and clear up some other bits and pieces. So next up, we're going to consider something we've made a big fuss of before, and that is that operators in quantum mechanics are linear. So linear operators. So, you know, what are the implications of this? So to explain this, I'm going to provide an example. It's also in the textbook. So we're going to consider some eigenvalue problem with twofold degeneracy. So I get to talk about degeneracy a little bit and remind you of what that means. So for example, let's say we've got a particle in a square, and the wave function solution here is associated with two quantum numbers, n sub x and n sub y. It's a function of x and y, and this solution is as follows. It's 4 over ab to the half sine n sub x pi x over a sine n sub y pi y over b. So here's our solution, and we can recognize that the energy is a function of n sub x and n sub y, and that's equal to h squared over 8m n sub x squared over a squared. So I'm not going to go into the derivation of this since it shows up in prior sections of the course. So this should be a little reminder. We've actually looked at a particle in a one-dimensional box and a particle in a three-dimensional box, so this is somewhere in between. Okay, but you know, in the situation where we have A is equal to B, so in that special situation, we're going to recognize the degeneracy, right? So we're going to recognize in that case, when this is true, that E sub 1, 2 is equal to E sub 2, 1. And that is equal to 5h squared over 8ma squared. So we can also think about the Schrodinger equation here. The Schrodinger equation h hat times psi 1, 2, by the way, is also equal to h hat psi 2, 1, which is equal to 5h squared over 8ma squared multiplied by psi 2, 1, which is equal to 5h squared over 8ma squared times psi 1, 2. So we basically know that you know, let's think about the eigenfunctions of this effectively two operator equations in here, but both of these eigenfunctions have the same eigenvalue. Let me write this out. So psi 1, 2 is equal to 4 over ab to the half sine pi x over a, because n in this case is equal to 1, multiplied by sine 2 pi y over a, okay, because in this case n is equal to 2. We can also write out psi 2, 1, that's going to be equal to 4 over ab, again to the half, the same constant in front, but now we've got sine 2 pi x over a sine pi, because now we've got the 1 in here, pi y over a. So what we recognize here formally is both are eigenfunctions having the same eigenvalue. So we started this particular slide by talking about linear operators, right? So what does this mean? This means that any combination of these two wave functions is also going to be an eigenfunction of the operator h hat with the same eigenvalue E12 equals E21, right? So basically any combination of these two is going to give us the same eigenvalue, right? So kind of think about that for a second. Let me write that in some sort of more general terms. In general terms, h hat C12 psi 12 plus C21 psi 21. That's really what I was trying to describe in the previous slide, is equal to C12 h hat psi 12 plus C21 h hat psi 21. Okay, we can do this because h hat is a linear operator. Okay, so another thing we can write down here, by the way, let's include the energy terms, the eigenvalues, okay, because now we know this piece in here is also equal to the eigenvalue 1, 2 times psi 1, 2, and similarly C21 E 2, 1, psi 2, 1. Okay, how else can we write this down? I'm now going to basically recognize that because E12 is equal to E21, let's put in here C12. Let's call this, well, we'll keep this as E12, psi 12, but over here we're going to put C21, E12, psi 21, and then lastly, let's bring the E12 outside the brackets, and inside the brackets C12, psi 12 plus C21, psi 21. So basically, what does this tell us, right? So if we think about this, we've basically got, so this also tells us, of course, that this expression, this must also be an eigenfunction. So that's kind of the importance of linear operators, and we'll see this come up later on when we think about expanding the solutions, the quantum mechanical solutions for atoms into molecules. Okay, that's another little piece wrapped up. On to the next one. So at this point, I'm going to scare you a little bit and say, let's remember the general definition for a Hermitian operator, but we're not going to spend too much time on that. I'm going to actually use it to introduce something called the BRA-KET notation. So we'll come to that, and the point of this is to come up with a notation that saves us a lot of time and a lot of ink. Okay, so let's come back. So we have a jumping off point. Let's come back to that more general definition of a Hermitian operator. So this is the piece that you really need to learn. Here is that definition. So we've got this function f of m star. Sorry, it's f of x, some quantum number m. Here's our operator, and we've got another another function in here. It's a quantum number n, or state n, f of x dx, and that is going to be equal to, for a Hermitian operator, it's identical to f of n multiplied by the operator, the complex conjugate of the operator, multiplied by f of m of x, this complex conjugate of f of m dx. So there's a new way of describing the general definition of a Hermitian operator. And we'll also say here, by the way, that where f n of x and f m of x are well-behaved functions. So let's introduce this BRA-KET notation by rewriting this. And here we go. Going to now write exactly the same thing, but using the BRA-KET notation. And this is equivalent. So this BRA-KET notation is equivalent to the integral over the full range here, f m of x, and that's the complex conjugate is on the left hand side in here. So that's the complex conjugate. Here's the operator a hat, f of n dx. So effectively, the fact that we've got these brackets here around the brackets themselves represents that we've got this the integral. Okay, we've got our operator that sits in the middle in here, and a left-leaning BRA basically says this is the function associated with m that is the complex conjugate on that left-hand side. So this we call the BRA in here, and here we call the KET. And of course, we're just introducing here right now, so we'll see more of this BRA-KET notation later on, so I'm just planting another seed. But how would we rewrite our expression at the top here associated with this Hermitian operator? Well, just restating what we have at the top here, we know that this is equal to this right-hand side in here. How do we write that in the BRA-KET notation? Well, that would be written in the following way, where in this case we actually put the complex conjugate sign after the BRA-KET notation, because effectively we're just flipping everything around. We've got, usually we're expecting the complex conjugate to be on the left hand side, so in this particular case we don't have a complex conjugate on the left hand side. Usually we're not expecting complex conjugates on the right hand side, but we are. The star here denotes that I have a complex conjugate, in fact, that's here and here. So it kind of makes sense. So this is the way that we would write and define a Hermitian system or Hermitian operator, exactly as I'm writing here, and you will see that it is rather quick to do. And so we want to get familiar with that particular way of writing in this shorthand approach in here. So that's another bit and piece that we need to be aware of that comes in from chapter 4. Moving on again, a couple more things. So we're going to now talk about something that's actually critically important. So orthogonality. What we're going to do is consider two eigenvalue equations. So those eigenvalue equations are as shown. What we're going to do is we're going to multiply, let's call this equation number 1, by the way. Let's call this equation number 2. So these are eigenvalue equations. What we're going to do is we're going to multiply number 1 by psi m star, and we're going to integrate. And so what do we end up getting? We'll get psi m star a hat psi n dx. And this is now, of course, equal to, we're doing the same thing, by the way, to the right hand side. That's equal to psi m star a n. In fact, we can bring the a n outside. Here's our constant, so we bring that outside the integral. And now what we do is take the complex conjugate of 2. So we're going to look at our expression here and take the complex conjugate of 2. And then we're going to multiply by psi n and integrate. So let's do that all in a different color. Let's write down what we're going to do. Take complex conjugate of 2 and multiply by psi sub n and integrate. Okay, let's do that. So we're going to multiply by psi n. We're going to take the complex conjugate. So we end up with a hat star psi m star dx, and that's equal to, well, we've got to have the complex conjugate at the other side. So that's a m star. That's going to come outside of our integral. And of course, inside the integral, we still have the psi n in here. And we also have the complex conjugate of that psi m in here. And that's with respect to dx. We can, by the way, write that around in the other direction. Psi m star up front here times psi n dx. There's no operator in there, so we can reshuffle those, if you will. Let's make sure we've got the a sub m star there at the front. Of course, we've just talked about this Dirac BRA-KET notation. So another way of doing this perhaps is to actually write this using that BRA-KET notation. Let's do that just for a little bit of practice. So what do we have? We've got at the top here, we've got m a hat n equals a n, and then in here we're going to have m and n. There is in the integrals, but there's no operator in here. We've also got from this section in blue in here, we've also got, let's put the colors kind of the same, so we've got n a hat m in here, and then we're putting the complex conjugate in here. Don't forget, usually we're expecting the complex conjugate to be here, okay, but we're not seeing that at the moment. That's why the whole piece in here, this whole direct notation, has the complex conjugate sign next to it, and that is equal to, and now we have a sub m star, and then inside we've got m n, just like before. So we've got the same integral piece, the same thing inside the Dirac BRA-KET notation down here. Okay, so where are we going with this? We're going to subtract one from the other. So let's subtract one from the other. So what do we end up with? Minus n. So we're just factorizing down there at the bottom. Now, if the A is Hermitian, which it is if it's a quantum mechanical operator, then we know, change color again here, you know where we're going now with this. So we're basically saying that if A is Hermitian, then this expression in here is equal to this expression in here, and therefore this left-hand side up here is equal to 0. So that left-hand side is equal to 0, which means that the expression here on the left-hand side is equal to 0. So this must also be equal to 0. So there's two possibilities, right? We've either got, let's turn this over to the next slide. But basically what I'm going to say is we've got this first term could be 0, or this second term could be 0. So let's have a look at those possibilities. So what I'm saying is either of these terms will be equal to 0. Of course, reminding ourselves of the Dirac BRA-KET notation, the term on the right hand side, dx, is equal to 0. This is kind of what we're saying is one of the particular cases that could possibly happen. But let's explore this in a little bit more detail. So actually, I'm going to provide you with two cases, and one of those cases is the case where we say, well, actually, let's take mathematically the case where n is actually equal to m. So this is a mathematical case, and in this particular case, right, where n is equal to n, this is actually our normalization condition. So if we, for example, consider that m is equal to n in here, then this is our normalization condition. So we'd write this as shown. And therefore, in this particular case, a sub n minus a sub m, we'd say that would have to be equal to 0, but note as well, that would also be the same as saying a sub n minus a sub n star,
which is also equal to A sub m minus A sub m star. So what can we learn from this? Effectively, we're saying here, okay, this means that the eigenvalues have to be real. In other words, this complex conjugate has to be the same as the original eigenvalue. So this means, and this makes sense to us because eigenvalues have to be measurable, so we can't have a complex number for an eigenvalue. So this is quite an interesting conclusion from this case 1 situation. What about, let's talk about case 2. And in case 2, we're going to say, okay, n is not equal to m, and we're going to work from a general situation that the system is non-degenerate. Okay, so there's no expectation that the system should be degenerate. So let's formally state that the system is non-degenerate. So what does this mean? Basically, in that particular case, we might expect in that particular case that A sub n minus A sub m, all right, is actually going to be non-zero, right? So that's the assumption here. So this therefore means that our integral over the wave functions multiplied by themselves integrated over all space, so that is equal to 0. This must be true. And so this has a particularly important ramification. This is called orthogonality, and it's a property again of all wave functions in the same system. So let me just explain again using the particle in a box description to help me illustrate. So we'll go to the next slide. We're going to remember that it's this integral that ends up being 0, and we're going to ask ourselves, what's the physical meaning of this? So if we think about our particle in a box, and we imagine psi 1 in here, and we're going to imagine the second wave function here, psi 2, the second state, if you will. So let's now consider that case where over all space, in this case will really just be inside the box, the limits of being a and 0 here, we have got psi 2 star psi 1 dx, and we're saying that this must be equal to 0 when n is not equal to m, and these are certainly not degenerate wave functions, or they're not associated with degenerate energy levels. So we can, by the way, straight away observe that this integral is correct. It is equal to 0. We have an integral, if we multiply, if we draw a kind of line down here splitting the two, then when we multiply these together, we've got a plus value up here in this segment and a minus value in here that's equal and opposite to that. And so when we sum those two together, when we sum the multiplier of those two functions together, we do recognize that the green region in here is exactly the same, but opposite in sign to the red region in here. And so those will cancel each other out. That will give us the 0 value in here. So that's the reality. So we're going to observe that this happens for every wave function within a certain system. That orthogonality occurs for psi 1 and psi 3 and psi 277, etc. And the point here, that the physical meaning that we're going to take away from this, is that the particle, in this case is a particle, cannot be in two energy levels. Can't be in two quantum states, really, at the same time. So this is pretty important. We can't have an electron be in two orbitals at the same time. We can't have a particle be in two quantum states at the same time. So in this particular case, when we have this non-degenerate system, we know it's non-degenerate. So these energy levels are different to each other. And so we can't have a particle have two energies at the same time. And that's a really critical thing that comes out of this orthogonality condition for two different eigenfunctions. That's the key. So lastly, by the way, we used the fact that our operators were Hermitian to help us derive this case for orthogonality. But the key point I'm going to finally write at the bottom of this slide. So a set of functions, both normalized and orthogonal, is called an orthonormal set. And we can use something called the Kronecker delta to represent that mathematically. And here's how we describe this Kronecker delta. Let's put the full integral in here. And we'll include our BRA-KET notation. So here's the Kronecker delta. And delta nm is equal to, it's 1 when m is equal to n, and it's 0 when m is not equal to n. And there is some more shorthand for you. So every time we refer to a simplification of a mathematical expression using the Kronecker delta, this is what we mean. Just wrapping everything up, let's finally finish with a review of the time-independent Schrodinger equation. So this is given as postulate 5. We use this capital psi in here, which is a function of position and time. There is our time, this should say time-dependent Schrodinger equation. So we can do some separation of variables. We're going to say we've got a wave function piece that's a function of x, and we're going to have some function f of t in here. I'm going to say that's equal to our capital psi. So let's plug that in. So because we can separate these two, we're going to recognize that this is not a function of time. This little psi is not a function of time. We can bring it outside of the derivative. And then what we do is, of course, divide by psi. And we end up with, so of course the Hamiltonian operator also doesn't have an operator associated with time in there. So let's pull out the function of time. Next, we're going to divide by the full function. So we're going to divide by this full function, and we therefore get 1 over psi sub x, or psi x rather. And so from that, we get 1 over psi of x h hat psi of x is equal to the energy. And this is really, what is this? This is our time-independent Schrodinger equation. When we rearrange this expression, right, so this psi comes up over here, so there's our standard time-independent Schrodinger equation. And so what happens when we work with the other side in here with the time piece? So we also get df of t by dt equals minus I over h bar e f of t. That's because, of course, both of these sides were going to be equal to that common constant, and that's according to the separation of variables approach that was introduced in chapter 2. So we basically bring the f of t up over onto the right hand side, we bring the h bar over to this side as well, and we also we're going to divide by I, and so when we have 1 divided by I, we end up getting minus I. So that's how we get this expression. And so what we can recognize here, that the solution here, the time-based wave function, is equal to e to the minus I et over h bar. And the final expression, if we want to write that all down together, our final wave function, psi of x and t, is equal to the position wave function psi of x multiplied by e to the minus I e times time over h bar. And there is the final eigenfunction, the final way that we can write down the full wave function for the system that we're considering. So those are just some notes there on the time-dependent Schrodinger equation that ties up all the loose ends from chapter 4. That's it. Thanks for listening, and see you next time.